Good afternoon, everyone. I am Chanda Devnath, one of the PMRF fellows. So, I am pursuing my PhD from Mysore, Berhampur. I am the TA of this course named A Study Guide in Organic Retrosynthesis and Problem Solving Approach. So, in this course, in these classes, I am trying to discuss about some named reactions and some important reactions which may help you to plan any retrosynthesis of any compound. So, the previous classes also I was discussing some small name reactions. Here I also do that. So this is our 6th class. So in the upcoming classes, when all these type of important name reactions are completed, we'll focus on planning retrosynthesis of any compound. So let's start. So we have already discussed about all these name reactions. Today among them we will discuss about this Korechikov reaction and some other reactions also. So in the last class I was that we will discuss about olefination reaction next class. So today I will discuss all these olefination reactions. So the first one is Wittig olefination. So this is one of the important one. I hope many of you has heard this name that is called Wittig olefination. So in this case we use ylide and prepare olefin from ketone or aldehyde. So it is an organic reaction where an aldehyde or ketone are heated with a phosphorus ylide to produce an alkene. So ylide means when there is a positive and negative charge adjacent to each other, that is called ylide. And phosphorus ylide means one of the atom in ylide is a phosphorus. So this is our phosphorus ylide with a positive charge on phosphorus and negative charge on carbon, and this carbon will attack to this carbonyl compound and form this alkene. This is called Wittig reaction. So if you see the mechanism, this phosphorus ylide, the negative charge will attack to this carbonyl compound, it will open up, O minus will form, it will attack again to this positively charged phosphorus. As we know, phosphorus is a vacant d orbital, so it can take electron. So that's why it is taking electron from oxygen and forming this betaine intermediate. After that, this is a betaine intermediate. After that oxygen attack, it forms an oxophosphatide intermediate, and through ring cleavage, it forms this alkene, and as a byproduct, it forms phosphine oxide. So there are two types of ylide. One is stable ylide, another is unstable ylide. So what is called stable ylide? Suppose you have this structure. This is called ylide, right? One side is positive, one side is negative. So if you have a group here which is electron withdrawing, then this negative charge will be delocalized. That means the ylide will be stabilized. And if you have electron donating group, then it will push the electron towards this negative charge. So that means the negative charge will be destabilized. That is called unstable ylide. So there are two types of ylide. One is unstabilized ylide, another is stabilized ylide. So unstabilized ylide has normal this methyl group, which is a electron donating group due to its plus I effect, and this negative charge here get unstabilized. So this is called unstable ylide. Whereas in this case, the negative charge here, if you imagine this like the open model, which I already showed, because of the resonance effect of the phosphorus d orbital, it present as like this double bond, but you can imagine it like this way also. So this negative charge has a adjacent ester group, which is a electron withdrawing, which is a electron withdrawing group. Because of that, this negative charge gets stabilized. So this is called stable halide. Now, what is the difference? If you use a stable halide and if you use an unstable halide. If you use a unstable halide, you will always get a Z alkene, that is a Z alkene, when the two higher priority group are same side of the double bond. And if you use a unstable halide, you will get a E alkene, where these high priority group are opposite to each other. Okay. So the reason behind getting E and Z alkene, that is due to its stereochemistry. So that I'm not going into details. If you are interested, you can go and read from Claydon. It is in Claydon, and also from Kaisan work is also a good book. You can go and check from there. So I'm not going into the details mechanism. Just remember, for shortcut to solving any question, if the halide is stable, you will always get a C alkene, and if that is a C alkene or C alkene, and if you get a halide is unstable, you will always get a E alkene. So what will be the product here? So you have to see your your halide is stable or unstable. That is the main goal, main thing you have to notice in every question. So if you just draw an open model, so it is like this. Now, due to presence of this allylic group, this negative charge can be delocalized. Therefore, this is a stable halide. This negative charge can be delocalized, so that it is a stable halide, and stable halide always give a E alkene. So the product will be, I'm just drawing it as a ER. This total, I'm denoting as a ER. So this will be our product. Newly formed alkene will be a E alkene. So this is our newly formed alkene, this one. So this is a newly formed alkene is a E alkene. Next, if you add H3O plus, what will happen? Obviously, this is a aldehyde protected group. So the aldehyde will be deprotected. So this will be our product. Okay. Why now if like why they have done this deep protection? Because suppose you use this one as an unprotected in not in a protected form, what can it can react with its own molecule? That's why they use this as a protected form. So what will be the product in this case? So you have to determine the halide nature first. So there is a negative charge here. So there is no such electron withdrawing group at this place. Because of that, it is a unstable halide. This is an unstable halide. So it will give a E alkene. It will give it will give a Z alkene. It's not a stable halide. This is a unstable halide. So it will give a Z alkene. So if you draw the product, so this they had the negative charge will attack to here. There is no such, so it will undergoes an intermolecular reaction. It will open up. The then there will be a formation of double bond from this place. So this will be our product. This is a newly formed alkene is a Z alkene or Z alkene. Understood? Suppose they use a stable halide in this case. They use a group here, a ester group like CO2T or something, and use a stable halide. What would happen? It would give a E alkene, but it would create a huge strain and it won't form a ring, because if you try to form a E alkene here, there will be a huge strain here. That's why they used a unstable halide. Now what happened in this case? In first instance, you might think there is no such halide. Then how the reaction will perform? So in this case, they have given a alkyl bromide and PPS3. So that means in medium the halide will form. In medium the halide will generate, and that will react with our ketone. So if we go step by step, this PPS3 in medium will react with this alkyl bromide. So this will attack here and bromine will be eliminated. Now there is a hydrogen here, and now if you add a base, in presence of base, here the base is NaH, so this H minus will take a proton from here and remove as H2 gas and generate a negative charge here, and that means it's forming a halide. It's forming a halide here. Okay, halide here. Now this halide is electron donating or a stable halide or unstable halide. So there is no such electron withdrawing group. So this is a unstable halide. So this negative charge center will attack to this carbonyl and form a alkene product. So if you see, so this will be our product. I jumped some steps. I hope you have understood. Okay, so this will be our product. So they have given two reactions with two different halide. What will be the product? So let's draw in a open form just to know what is the nature of the halide. So there is a hydrogen group here, whereas there is a methyl group here. So between these two, which one is more unstable? Obviously this one, because it has a methyl group here, so it donates some electron towards the carbon. So this center is bit stabilized than the unstabilized than that one. But in both the cases we have a ester group. In both the cases we have a ester group. That means we can consider them as a unstable halide. So let's, what will be the product here? It will form this alkene. The next, okay, what will happen here? It will also form a alkene. So nothing is, there are two groups here. One is CO280, one is CH3. You have to, so there will be two groups. You have to place the groups such a way that it would get E alkene. So if there is, this is the bond, so CO280 will be at this place and methyl would be at this place, so that it can maintain its E stereochemistry. Okay. Next olefination reaction is Peterson olefination. So this is similar type of olefination, but instead of the phosphorus halide, here we will use a silicon halide. So the reaction involving the addition of a alpha silyl carbanion to the carbonyl compound aldehyde or ketone to form a beta silyl alcohol, followed by elimination of silyl yields alkene. Such reaction is called Peterson olefination reaction. This reaction is known as a Peterson elimination reactions also, or olefination reactions also. So this is called sulfur halide, is a silicon halide. So this will attack to this carbonyl compound and form this beta hydroxysilane, and if it can be catalyzed by acid or base to form this alkene. Now if you add acid, the product will be different. If you add base in this step, after this formation of the silyl alcohol, if you use acid, the product will be different. The stereochemistry of the product will be different, and if you add base, the stereochemistry of the product will be different. So in Wittig, how can you control the stereochemistry of the alkene? By changing the stability of the halide. If the halide is stable, it will give a E alkene. If the halide is unstable, it will give a Z alkene. But in case of Peterson olefination, how can you control the stereochemistry of the product? By controlling the condition. If in the next step the reaction is acid catalyzed, you will get a one type of product, or if it is a base catalyzed, you will get a different type of product, like different stereochemistry of the product. So let's see the mechanism. If it is a base catalyzed, how the reactions take place. So up to this you have understood, right? This negative charge will attack here and it will open up and form a negative OH. So this carbon-carbon bond forms. Now if you add a base, this OH will be deprotonated and this O minus will attack to this silicon. Similar to, just compare with the Wittig reaction. Just similar to like the phosphatane, the betaine intermediate and oxophosphated intermediate. So this is kind of like a beaten intermediate. After that O minus will attack and it will form an oxophosphated intermediate, and it undergoes similar type of ring cleavage to form this. So if it is a base catalyzed reaction, it always undergoes a C elimination, because to formation of this cyclic intermediate, you always need O minus and silicon at the same plane. O minus and silicon at the same plane. So that's why it undergoes a C elimination. But in case of acid catalyzed, this OH get protonated, form a good living group as water, and then it through trans elimination, this carbon silicon bond breaks and this eliminates from the system. So if it is acid catalyzed, it will always give a trans elimination. So if the reaction is a base catalyzed, it will undergo C elimination. The product we have to determine from the substrate, but substrate will undergo the C elimination. Whatever product will give, that is depending on the stereochemistry of the substrate, but substrate will undergo the C elimination and a trans elimination. Don't get confused with the Wittig one. Wittig, if the elide is stable and unstable, from that you can directly determine the stereochemistry of the product. But in this case, you have to know the stereochemistry of the substrate, because it doesn't mean ki C in elimination means C in product. C in elimination will take place, but the product stereochemistry will depend on the substrate. Understood, right? If I give some examples, then you will get an idea. So in this case, there is a negative charge here, so it will attack to this carbonyl and it will open up. Now in this case, the stereochemistry is not in concern, because we don't know the stereochemistry of the substrate here. So that's why it undergoes a as it is acid catalyzed, it will undergo a trans elimination. Just consider that. And this will eliminate it. As this ring is totally equivalent, if you would consider, if this is not, there is no such stereochemistry is maintained here, so you can draw it anyway. You understand what I'm trying to mean? Because as the stereochemistry of the substrate is not mentioned here, and both the site of the double bond is equivalent, that's why they can't determine the stereochemistry. This and these are equivalent to each other, so that's why you can't determine the stereochemistry in this case. So what will happen here? So there will be negative charge at this carbon and attack to this. Now the thing is, the adjacent methyl is above the plane. The adjacent methyl is above the plane. So obviously this will come from the below the plane. It will come from the below the plane. The adjacent methyl is above the plane. So this will come from the below the plane. So the O minus will be, the oxygen will be open up from to the above the plane. So this OH will be above the plane. So it will undergo the elimination in presence of acid. In presence of acid. And gives this as a product. Okay, the other stereochemistry will be written, so I haven't drawn this. All this part will be same as the substrate, so I am not drawing it. Okay, let's go to the next one. Next is Julia olefination. So aldehydes or ketone react with a sulfone in presence of base to produce an adduct which on treatment with acetic anhydride gives an acetyl derivative that undergoes a reductive elimination in the process in the presence of sodium amalgam and to yield alkene. Such type of reaction is called Julia olefination. So there is a sulfone. So the sulfone in presence of base, it will take up a proton here and generate a negative charge. This negative charge will attack to this aldehyde center and through acetylation of the OH group, it undergoes elimination reaction and gives a alkene. In case of Julia elimination, you will always get a E alkene. There is no such controlling effect. So if you want a E alkene, just without using with any type of reagent, it is not reagent dependent or substrate dependent. In that case, use Julia olefination because it will always give a E alkene. So this is the mechanism why this negative charge will attack to this aldehyde center, form this beta hydroxy sulfone. After that, it undergoes an acetylation reaction and form a good leaving group OAC. Then after that, it will get removed from the system. After that, this sodium one electron will be transferred to the sulfur center. This bond will break and form a radical. This radical undergoes a ring bond cleavage and remove the OAC from the system and form this E alkene. So what will be the product here? So in presence of base, there is a proton here. So in presence of base, that will be taken up and it will attack to this aldehyde and acetylation will be performed. So and in presence of sodium amalgam, that will be removed. So if you just draw step by step. In presence of sodium amalgam, it undergoes acetylation Now in case of sodium amalgam, this will get removed from the system. What will be the product here? Now in presence of NHMDS is a base. This is a base. This is a base. Now there is a negative charge. There is a proton here that will be taken up and generate a negative charge here. So this negative charge will attack to this aldehyde center. And through same type of reaction, it will undergo the olefination reaction, and as in case of Julia, you will always get a E alkene. So it will always give a E alkene. Now it will form an alkene from this center. There is another hydrogen, so that hydrogen will be placed here, and this total big group, if you consider this as a R, this will be placed at this place so that it can maintain stereochemistry as a E stereochemistry. Okay. Next reaction is McMurray reaction. This is one of the olefination reaction when two ketone or aldehyde coupled with each other to form an alkene. In this case, you don't need another reagent. Just in presence of titanium reagent, these two aldehyde or ketone just combines to form an alkene. This is the mechanism where this titanium chloride and zinc react with each other to form titanium chloride. This titanium chloride react with the alkene. First, it will give one electron to this oxygen and it will open up and form a radical intermediate. Then it will react another molecule of aldehyde. After those, it undergoes a homocoupling, and through cleavage of this ring bonds, it will form this alkene. So there is one reaction here. What will be the major product formed in this reaction? Just remember the mechanism and try to draw it. Try to get an idea what will be the product in this case. As I said, the titanium will be coordinating with both the, in case you see, coordinating with both the aldehyde and form this intermediate. So that means for forming this during forming this intermediate, these two OH groups are at the same plane. These two OH groups are the same plane. After, in the next step, you need a heat. You need a heat for cleaving of this, for the cleavage of these ring bonds. Suppose you just perform the reaction at room temperature. What will happen? Just this oxygen titanium bond will cleave, which is the weakest bond here, instead of the carbon oxygen bond. So it will form a syn alcohol. So this form a syn diol. It will form a syn diol. So the similar thing will happen in this case also. So what will be the product? The product will be this syn diol. The product will be this syn diol. Next, Olefination reaction is Tebbe reaction. This is similar to that Wittig reaction, but Wittig reaction can only olefin can be formed from aldehyde and ketone. But by using this Tebbe reaction, we can form olefin from ester, amides, alcohol. In all the carbonyl compounds, we can form alkene. So this is called the Tebbe reagent. It formed by this is called the Tebbe reagent. In medium, it will form this ylide type of substrate where this is positively charged and this is negatively charged. This ylide type of complex. So that will react with our all the carbonyl compounds to form the product. So this is the reactivity order. In this Tebbe reaction, the ester's reactivity is higher than that of the aldehyde and ketones. In case of Wittig, reaction was always taking place on aldehyde and ketone. Esters usually don't react, but in case of Tebbe reaction, ester will react at a faster. The ester will also give the product, and acid alcohol will react. Then after that, this is the reactivity order of the Tebbe reaction. So what will be the product in this case? They just written as a Tebbe reagent. You know that what is the reagent now. So suppose I am just drawing it for you simplicity. This is our Tebbe reagent. So what will be the product here? So there is a ylide negatively charged here. So it will react with ester. So there will be alkene formation at this place. So the product will be this will be our product. Okay. Now what will happen in this case? Here also there are two carbonyl compound. One is ester and another is this one is ester and this one is amide. So which will react? So from the list you can see amide has more reactivity than ester. Amide has higher reactivity. Amides have higher reactivity than ester. So this amide will react first. So this will react first, but here the Tebbe reagent has been added in excess because 5 equivalent has been added. So that means both the carbonyl will be olefinized. Now suppose you are given one equivalent, then what would react? The amide would react faster than that of the ester. As here the reagent is in excess, 5 equivalent reagent has been added. That's why it will olefinize both the amide and ester. What will be the product in this reaction sequence? So from the reagent you can see this is a silicon ylide. This is a silicon type of ylide. So that means it is a Peterson olefination. This is a Peterson type of olefination. And so what will be the product? So let's draw it. it will undergo the olefination reaction. From this place it will attack. There will be alkene. Now in the next step they have added TBAF. So it is a fluoride source. TBAF fluoride source always generate a it will always deprotect these silyl esters. So it will attack to the silicon center and this OH will be deprotected. So there will be this alkene. And this OH will be deprotected. Now what will happen in this case? If you remember one of the previous classes, I have talked about Apple reaction. I know some of you has already I have already discussed about Apple reaction, which is used for substitution of OH group, because OH group is a bad leaving group, and if you want to substitute a OH group, we can perform this with the Apple reaction. So this is a reagent of Apple reaction. PCl4 PPS is a Apple reaction reagent. So what will happen? This oxygen will attack to this PPS3. It will form oxygen phosphorus bond. After that, the PPS3 will attack to this chlorine atom and it will form an intermediate like this. It will attack from the CCl4 and it will form an intermediate like this. Phosphorus will be positively charged. After that, oxygen will attack to this phosphorus center. And this will be removed. And then again, this chlorine will attack to this center and remove the OH from the system. Now it is always a SN2 type of substitution. So the newly upcoming chlorine atom will come from the above the plane, as OH group is already below the plane. If you know about the application, you go to my previous video. I am not drawing the mechanism in details here, or you can read from books also. So just the structures will be similar to that this OH will be just substituted by a chlorine and which will be above the plane. That is the main thing. The stereochemistry is the main thing. That's why they have mentioned the stereochemistry of the OH. Okay. So the whatever the OH group is in the plane in this, the stereochemistry will be different. Now you can get confused that why here in this step why the stereochemistry is not getting changed when OH is reacting, because in this case the fluorine minus just attack to the silicon center, not to the this carbon center. It is just attacking to this silicon center and reaction is taking place at this center. So the stereochemistry of this carbon is retained, but in the next step the chlorine is attacking to this carbon center. The stereochemistry is reversed. So this is one of the application of Peterson olefination in total synthesis. I just gave this so that you can get an idea why we have, this is important to know these small reactions to plan any retrosynthesis of any natural products. So this is a total synthesis. So where in the first step it will undergo the Diels-Alder reaction because there is a diene. If anyone doesn't know about Diels-Alder reaction, in the next class we will discuss that in details. So this is the diene and this is the dienophile. So it will combine to form a 6-member ring like this. It's a Diels-Alder reaction, 4+2 annulation. After that, if you add this reagent, silicon ylide, so that means a Peterson elimination, it will take place. So there is a aldehyde, there is a ketone center here and there is a aldehyde center here. So aldehyde has more reactivity than that of ketone. So this carbonyl will react than that of this one. So it will form this alkene, and after multiple steps it will form this natural products maritime. Okay. Next topic will be, so we have almost completed all the types of olefination reactions. So if you face this type of reagent, you can now perform, because in your assignments also there is the whatever questions have been given, there's based on some small reactions. Next is reaction of olefin. Now you have formed olefin. Now you know how to generate a olefin from aldehyde and ketone. Now next thing is, what is the reactions of this olefin? How olefins react? So I have included two olefination reactions of olefin here in this class. First one is this Corey-Jacobsby reaction and second one is Simon-Smith reaction. So what is Corey-Jacobsby reaction? Suppose you have sulfur ylide instead of phosphorus ylide. You are using sulfur ylide instead of phosphorus ylide. What will happen? And use this aldehyde or ketone. So if you have, there are two types of sulfur ylide, like similar to the phosphorus ylide. One is stable ylide and one is unstable ylide. If you use a simple ketone, suppose if you use a simple ketone and use both the ylide, if you use this sulfur ylide, what will happen? In this case, it doesn't form a alkene, rather than it form a epoxide. So this is called Corey-Jacobsby reaction. Now if you use a stable ylide instead of unstable, if you suppose this reaction is taking place for an alpha beta unsaturated ketone. Now instead of this simple ketone, you are taking an alpha beta unsaturated ketone and adding two set of reaction. One is unstable ylide, one is stable ylide. So if you are adding unstable ylide, the reaction will be normal like the other. The epoxidation will take place. But if you use a stable ylide, the carbonyl group will not react, rather than the alpha beta unsaturated double bond will undergo the cyclopropionation reaction. Okay, so this is the difference. So if you have a simple aldehyde or ketone, it will always give a epoxide. It will always give a epoxide. This doesn't matter which type of ylide you are using. But if you have alpha beta unsaturated aldehyde, and if you use an unstable sulfur ylide, it will give a epoxide. But if you use a stabilized ylide, it will form a cyclopropionation of the alpha beta unsaturated double bond. So this is called Corey-Jacobsby reaction. So they had given the one example. So this is our substrate. If you use this sulfonium ylide, that is the stable ylide, which group will react? Obviously this carbonyl center. So it will undergo the reaction, it will form a epoxide. Now if you add a stable ylide, sulfoxide ylide, because this negative charge can be delocalized to this sulfoxonium part. So this is called stable ylide. So the stable ylide will react with this alpha beta unsaturated double bond and form this cyclopropane. Now if you have used this different type of reagent, that is called Simon-Smith reagent, what will happen? So it will react always it will react with the electron rich double bond. So we know that alpha beta unsaturated double bond is not electron rich, electron deficient. So the other double bond which is electron rich, so it will react with that one. So from the same substrate you can get three different products just changing the reagent. So if you have sulfonium ylide, you will get a epoxide. If you give a sulfoxonium ylide, it will get a cyclopropionation of the alpha beta unsaturated double bond. And if you use the Simon-Smith reagent, it will undergo the cyclopronation of the electron-rich double bond. That is not alpha beta unsaturated. Whichever is electron-rich than that, it will undergo the cyclopronation of that one. So what I was talking about, the Simon-Smith reaction. This is a organic reaction. It's a stereospecific reaction because this is a single step one. This is the mechanism. I am not going into details. So what will be the product in this case? The major product form in the following reaction. What will be the product in this case? So this is a Simon-Smith reagent. So as this silicon is above the plane, it will create a huge steric hindrance for this large compound because zinc is there. So this is large compound, this will create a huge steric hindrance. Because of that, as it is a single step reaction, so as it is above the plane, this reagent will approach from the below the plane. So the cyclopronation will take place to the below the plane, and during the cyclopronation, the other stereochemistry of this double bond will be retained because this is a stereospecific reaction. As I said, the in this case also you have seen it's a stereospecific reaction. Suppose you have this double bond, there is no concerted reaction, so you have imagine this is a double bond here. So when the reagent is coming from the above the plane, it will just react with this two center. There is no such state where this double bond get cleaved and it get a chance to rotate the bond. So there is no such case of rotation of this alkene. So whatever the stereochemistry of the alkene in previous before the reaction, the stereochemistry of the alkene will be retained after the reaction also. So the cyclopronation will take place. Cyclopronation will take place from the below the plane, and the stereochemistry will be so. In both the cases, the cyclopronation is below the plane, but in this case, see the methyl group is just opposite to this one. That means it has been rotated. That is not possible. So the correct option is A. What will be the product? If you add A, what will be our product? If you add B, what will be our product? So A is, they have given the product, you have to determine the reagent. So by using A, the cyclopronation of this double bond. If you add B, there is cyclopronation of this double bond. That is the alpha beta unsaturated double bond. This is electron deficient double bond. Electron deficient double bond. So electron deficient double bond cyclopronation means the Corey-Jacobi reaction. So you need a sulfoxoniumylide. So the B should be a sulfoxoniumylide. So the option B, C, D, the B should be a sulfoxoniumylide. So this B, so A and D are already cut because B should be on a sulfoxoniumylide. So option will be among B and C. Now in the next step, they undergo cyclopronation of this electron-rich double bond. Now in one, they use this Simon-Smith reagent. In the next one, they use this sulfoniumylide. So sulfoniumylide can't never give a cyclopropane reaction, because in the examples I have shown, sulfonium ylide always give a epoxide. Sulfonium ylide always give a epoxide. So this is already cut. So the correct option is option B. Okay. What will be the major product formed in the following reaction sequence? It's a bit difficult. Just give it a try. Just give it a thought. It's not the simple ones like cyclopropanation or epoxidation. The reaction is a bit tricky. Just give it a thought. So what will happen in this case? So if you add a base, there is a proton here. So that will be deprotonated. Generate a negative charge. So that will come attack here. Okay. In the next step, this O minus will come here again. There's a methyl group here also. This O minus will come here, and this CH2 minus will attack to this methyl group, and this will be neutralized. So the product is, this is a bit difficult. Okay, just try to. Some reactions are substrate specific, right? So this reaction is bit substrate specific. There will be a methyl group here and a cyclopropane with the sulfur methyl. Now in the next step, if you add ranny nickel, in presence of ranny nickel, always carbon sulfur bond undergoes a cleavage. So the product will be this one. The correct option is option C. In presence of ranny nickel, wherever there is a carbon sulfur bond, that undergoes a cleavage, which I have shown in these examples also. If whatever in presence of ranny nickel, this undergoes a cleavage, so it will just you have to cleave the carbon sulfur bond, and in presence of ranny nickel, it undergoes a reduction. So this carbon-carbon bond undergoes a reduction also. So, but the aldehydes will be remain intact. The two aldehydes will be intact. Aldehydes do not undergoes reduction in presence of tiny nickel, but carbon-carbon double bond goes. We have read this in class 2, I think. So carbon-carbon undergoes a reduction, as well as the carbon-sulfur bond also undergoes a cleavage. See the substrate here. The bromine is not at the alpha position with respect to the ester. Still the reaction is happening. So try to get the reason behind that also. Just give 10 seconds. So what will happen here? So see, the bromine, this is the, with respect to this ester, this is alpha, this is beta. So bromine is not in the beta position. It's not in the alpha position. But still zinc can be incorporated here. Why? So the reason is, see, but if we consider this as a carbonyl type of system or any conjugated type of system, with respect to this is alpha. So that's why due to the extended conjugation, why like in the previous one, why I were talking that only beta alpha position is reactive for this center, because after you have seen that after the incorporation of the zinc, there is a resonance stability. There is a resonance stability with the adjacent carbonyl group. With the adjacent carbonyl group. Okay, there is a resonance stability. But if it is in beta, there is no such resonance stability. But in this case, if it get incorporated into this CBr bond, into this CBr bond, so there is a chance of resonance stability because of this extended conjugation. Because of this extended conjugation. Okay, that's why in this case, instead of being in the beta position with respect to the ester, the reaction will happen due to this extended conjugation. Okay, so what will be the, so this will form. After that, you have get an idea that in case of reformers, for which center is get the zinc bromine, that center will attack to this aldehyde. So when you are adding this aldehyde, so this center attack. Okay, we will get this type of, this center will attack, sorry, and we will get this type of hydroxy species. Or you can, for your understanding, I'll draw it. So this will form. Now as you have seen that this is not given in the product, so you have to think about the next step also. So as there is a hydroxy group and there is a ester group, so it can be replaced very easily. So what will be the product? So you can see, just try to match the product with the option. So correct option will be option C. So correct option will be option C. Okay. So this much of the reformatic reaction. First is we need a alpha halo compound which will get incorporated by the zinc and convert into a nucleophilic center, and that will attack to a carbonyl compound like aldehyde ester or acyl chloride or any alpha beta unsaturated compound. So this mechanism to form this type of compound product, and there is a modification due to less solubility in organic solvent. They have incorporated copper cyano reagent into that zinc species and form a mixed metal compound that will react with our aldehyde species or carbonyl species to give us our desired product. Based on this, one question came in GATE 2020, and in this way they got the same mechanism, they got their desired product. Okay. Now I have tried to discuss two extra questions which may come in the coming GATE years. So from that you will get have a practice also how to solve a question or how to get an idea about that. So try to solve this one. I just give 5 seconds. It is easy. By using zinc, there is a zinc species and there is a palladium. So you can, from that you can get an idea of Negishi coupling. Whenever seeing any zinc species along with palladium or nickel, you will just think about Negishi coupling. So just take 2 seconds and solve this. So let's start. So this is simple. Like whenever there is a living group type of species and palladium is there, so it will be easily incorporated into this RX bond. Then when you are adding this species here, so there will be a transmetallation type of reaction and we will get this center will combine with this center. Okay, so how many carbon? 3. Okay, 3 carbon. Then and this center, this part will be intact. Okay, so this will be our desired product. The mechanism is simple like the previous one. So next question is this one. I just give 2 seconds, try to solve this. See here they gave just zinc, no palladium, so that will be reformatted. So you have to notice the difference. Whenever there is a zinc plus palladium, that will be negacy. But when it is all palladium or zinc, nickel, but there is a two metal. But whenever there is only zinc, there is a chances of reformatted. So try to think in that way and try to solve this one. What will happen in this case? First, zinc will incorporate into this species and give us alpha zinc bromo species. And due to conjugation, it will give this type of system. And now when this ketone system is added, now you have to notice, see there is a double bond, but sometimes people does this mistake and whenever these options are given, they have given the options also like that way, so people can do the mistake. See, there is a double bond, but this is not in the alpha beta position. When the double bond is not in the alpha beta position, the Michael addition can't be possible. So see, if this is alpha, this is beta, this is gamma, delta, so gamma delta. So alpha, this Michael addition type of reaction is not possible. So the only possibility is into this carbonyl center, into this carbonyl center. So this one will here. So this is a thing to notice, because whenever we are seeing any carbonyl compound with a double bond, we think about Michael addition, but you have to notice the position of the double bond. So it is, sorry, I was just talking and I did the same thing. Position, and this will open up, and what we are getting, okay. Now see, there is a twist, as this center is alpha position to this ester, so this hydrogen is highly bit acidic. This hydrogen is acidic due to this resonance stability. This hydrogen is acidic.
and as adjacent to this there is a wedge group. This will come here. Get okay, this type of alkane type of species, alkene type of species. So this is our desired product. Okay.
So I'll just give an overview what I have discussed today. So we started with the olefination reactions. We have discussed all the olefination: Wittig, Peterson, Julia, Tebe, McMurray. Then we move to reactions of olefins, Corey-Jacobi reaction and Simon-Smith reaction. We solve some questions based on that. So in the next class, I will try to come up with some retrosynthesis of some molecules using whatever reactions we have discussed till now. Using those, how can we plan a retrosynthesis of any molecule? I'll try to come up with those. So thank you everyone. Have a nice day.